You are welcome to the Scholar online class. I will be your physics tutor for today. My name still remains Abdulwasi, and our topic for today is going to be on electric field. And what we'll be looking at under this electric field, we'll be looking at what electric field strength or electric field intensity. Just like when you talk about strength or intensity, it means what? The degree at which you apply either a force on something. So we define electric strength or electric field intensity as the force that is applied on what? On a unit charge. That is our electric field strength. That is our electric field strength. Electric field strength or intensity we represent with letter E is equal to what? The force F per unit charge. That is our charge Q. So mathematically, it means our electric field strength E is equal to what? Force over Q. And if you cross multiply, it means our F is equal to what? E or QE. That means this is relation between what? Your normal force and your electric field strength. I hope that is taken. Now, we can take this further from our Coulomb's law to arrive at what? A standard formula for the electric field strength to what? To a unit charge, or at a point to a unit charge. You know that we said from electrostatic force or from a Coulomb's law, our F is equals to K Q1 Q2 over R squared. Let's call this equation 1. And we also said that our what? F is equals to QE. Let's call this equation 2. Since the first one is force and the second one is force, when we bring it together, it means we are going to have what? KQ1 Q2 over R squared is equals to QE. And invariably, let's say the Q is just uniform. So one Q cancel one Q on the other side. That means we are not going to have what? Therefore, our electric field strength E is equal to what? KQ over R squared. This formula is very, very important. Or we can have it as what? E is equals to 1 over 4 pi E naught times Q over R. This is the electric field strength what? Per unit charge. As you know that our K is given on the board as what? 1 over 4 pi E naught. Where our E naught is called what we call electric permittivity of what? Free space or vacuum, which is 8.85 exponential minus 12 farad per meter. Let's take example on this also. Now, as you can see on the board, they said what? An electron of charge minus 1.6 exponential minus 19 coulomb experiences a constant force of magnitude 3.2 exponential minus 7 Newton. We have to calculate A, the electric field intensity, and B, how far is the electron from the field. Now, just like we did earlier, the first thing is to what? To bring out the given parameters. So, what are the given parameters here? We are given what? They say an electric, we are given the charge. Q is equals to minus 1.6 exponential minus 19 coulomb. The force is also given as 3.2 exponential minus 7 Newton. What are we asked to calculate? We are asked to calculate the electric field intensity, our E, that's the first part, and the distance, R, that's the second part. So since we have all the parameters now, you can now see that the formula that is suitable for this is for the first question, we are going to use our F is equals to what? QE, or E is equals to what? F over Q. Since the force is stated, is given, and the charge is also what? Given. So applying that, our force is 3.2 times 10 to the power minus 7 Newton, and our charge is what? Minus 1.6 times 10 to the power what? Minus 19 coulomb. So it means that the unit of electric field intensity is what? Newtons per coulomb, and is also what? Is also a vector quantity. So by interpolation, when you solve these two together, this will give us 2. That is minus 2.0 times 10 to the power what? That is 19 minus 7. And therefore our E, Newtons per coulomb. Our E is going to be what? Minus 2.0 times 10 power what? 19 minus 7 will give us what? That should be 13 newtons per coulomb. So this is what? This is the electric field intensity. Now, to the last example, still under what? Electric field strength or intensity. Now, we have two similar but opposite point charges, Q1 and Q2, each of magnitude 5.0 times 10 to the power minus 8 coulomb, are separated by a distance of 8.0 centimeter in a vacuum, as shown in the diagram above. Then we are asked to calculate the magnitude and direction of the electric field intensity. We are still following the same trend here, the same procedure. But this one has a peculiar case, in the sense that we have to use the diagram to illustrate what we have to do. Now, this is the diagram here. We have two charges in this form. This is my Q1, and the second one is what? Our Q2. This is my Q2, this is my Q1. Then we have P in between them. The distance here is 5.0 centimeter from P, and the second one is what? 3.0 centimeter from this point. So we have to calculate the what? The magnitude and direction of electric field intensity at P. But before I go to this, let me quickly explain something under the concept of those things that affect the electric field intensity. Now, three things affect electric field intensity. The first one is the nature of the charge. The nature of the charge. When we talk about the nature of the charge, before we go to that question, nature of the charge. When we talk about the nature of the charge, here we are talking about either positive, or positive, negative, or negative, positive. So if you look at these three, we are going to look at these three. What will be the effect of electric field intensity when it comes to what? These charges. Now, looking at the first one that we have here, that is when the charges are of what? Like charges. We are going to look at two scenarios here. The first one is like charges. Just like I stated earlier, like charges, according to the law of electrostatic force, what? Repel each other. So let's look at this here. Let's say this is my Q1 and this is my Q2, and I have P in between them. Now, this P is what? Is a neutral force. So because this P is a neutral force there, when this positive come to this positive, come to this P here, the charge will what? There will be what? Repulsion. There will be repulsion. So as a result, it means that what? This charge Q will be moving what? Away from P, and you have it the direction either this way. Or sorry, it means that our P will be moving away from charge Q1. Our P will be moving what? Away from charge Q. That means the Q1 will push the P away, because they are what? If we take this as a neutral, then this one is going to be repelled by this. Likewise, since our Q2 is also positive, also our P will be repelled away from Q2, and we have this moving inward also. So, and according to your knowledge of forces, since we said our electrostatic force, electrostatic field strength is also what? A vector quantity. According to the knowledge of force, when two forces are moving in the same direction, their resultant will be what? The addition. But when two forces are moving in opposite direction, their result will be what? Subtraction. So since these two are what? Moving in opposite direction, then our resultant electric field, we have E1 here for the first one, and we have E2 for the second force. So our resultant, the resultant electric field strength, that is our E, is equal to what? E2 minus E1, provided that E2 is greater than E1. That is for the first one. So for like charges, when they are moving, they repel each other, and their resultant will be what? The subtraction of the electric field intensity for what? For each of them. Then in the second case, when for unlike charges now, unlike charges. Unlike means what? The charges that are opposite. So let's say we still have this way. This is my Q1 negative, and this is my Q2, which is positive. And we have P in between them. In this case, let's start with our negative charge, Q1. Since this is negative and we have to have P just like we said earlier, for a body that is neutral at the point here, you take a natural charge of positive. So because this is positive and this is negative, what do you think will happen? That is what? Attraction will take place. So P will be what? Attracted to what? To Q. But for the second scenario here, this is positive and this will take this as also positive. Positive, there will be what? Repulsion. That means what? This one will also what? Follow this direction. That means what? P will be repelled. That is why the arrow is pointing in this direction. Our major focus is the P, not the charges here. So also here, for the charges Q2 and P will be repelled by this charge Q2, and that is why the arrow is moving inward. Why for this first one here, again, look at this negative and this positive. P will be what? Attracted to Q1. That is the charge is force. That's why the arrow is pointing in this direction. So for this case, the resultant, our resultant electric field, E, is going to be what? The addition. Because according to the law of force, when they are moving in the same direction, you add. That will be what? E2 plus E1. So this concept is what we are going to use to answer the question 3, the question 4. Now back to the question 4. We said that what? Two similar but opposite charges, Q1 negative and Q2 positive, right? Are what? Each of magnitude 5.0, that is our Q1 is 5.0 times 10 minus 8 coulomb, and Q2 is also what? 5.0 times 10 minus 8 coulombs, right? Okay, are separated by a distance of what? 8.0 centimeter. That means the distance between Q1 and Q2 is 8 centimeters. In a vacuum, I've shown the diagram. This is the diagram. We have to calculate the magnitude and direction of what? The electric field intensity. Okay, so this is the diagram. Let's now see the application here. So what we do is what? Just like the concept, let me explain this. Still applying the concept here. Q1 is negative, Q2 is positive. So what do you think will happen here to P? It means that P will be attracted to Q1 and P will be repelled away from Q2. So it means the arrow will point what? In the same direction, which means you are going to apply the second formula that I have on the board. So following that concept here, our E1, that is for charge Q1, is going to be what? KQ1 over R squared. And our R squared is what? The distance 5 centimeters, which is what? 0.5. So following that, it means my E1 is equals to KQ1 over R squared. And that translates to what? 9.0 times 10 to the power minus 9. Our Q1 is what? 5.0 times 10 to the power minus 8. Divided by the distance is what? 0.05. Converting that centimeter to meter. And that gives us the force parameters, which is same as 9 times 5 divided by 25 times 10 to the power. Okay, we have 9 times 5 times 10 to the power minus 8 times 10 to the power minus 9 divided by 5 times 10 to the power minus 2 squared. That translates to 45 times 10 to the power minus 17 divided by 25. That's 5 times 5, then times 10 to the power minus 4. So when you do this, you get your answer for E1. Likewise for our E2. Our E2 is also what? KQ2 over R squared. That translates to 9.0 times 10 to the power minus 9 times Q2, still the same magnitude, 5.0 times 10 to the power minus 8 divided by R squared. The distance is now what? 0.03. Converting that centimeter to meter, you divide by 100. So when we do this also, this will translate to 9 times 5 times 10 to the power minus 9 times 10 to the power minus 8 divided by what? 3 0.0 times 10 to the power minus 2 all squared. And that gives me C45 times 10 to the power minus 17 divided by 3 squared is 9. And this will give us 10 to the power minus 4. So finally, the resultant, therefore our resultant electric field strength or intensity E is equal to what? E1 plus E2. That is the addition of these two answers. That is, our E is equal to our E1. The result is this: 45 times 10 minus 17. So if you do this, minus 17 plus 4, that gives us what? Minus 13. So we have 45 over 25 times 10 to the minus 19 plus our E2. That is what? C45 over 9 times 10 to the power minus 13. So when you do this together, then you have your answer in newtons per coulomb. Now, the last aspect of our topic is electric potential. What do you mean by electric potential? Just like when you talk about somebody having a potential, it means somebody has what? That hidden strength in him, which has not been established. So when we talk about electric potential, we define electric potential as the work done per unit charge. So our electric potential is defined as the amount of work done to take a unit charge from a point to another. That is, electric potential V is equal to W, which stands for work done, over charge. So when you cross multiply, it means our W, the work done, is equal to what? QV. This formula also is very, very important when it comes to what? Electric field. If you have to calculate the work done, it means our W, work done, is equal to what? The charge times what? The electric potential. Likewise, this electric potential can be expressed in the other form, just like we have in our electric field intensity. So we can also have our electric potential V as 1 over 4 pi E naught times Q over R. 1 over 4 pi E naught times what? Q over R. Remember that this one is just R. Y for electric field intensity is what? R squared. So from this now, then we can proceed in our subsequent lesson. But with this, I think we're able to establish what we mean by electric field and the basic concept, which is what? Coulomb's law, the electric field strength or intensity, the electric potential, and all the formulas are what? Interwoven, which means that one relates to the other. So hope to meet you in our next class. Thank you.